Hello, Brandon. This is going to be part one of the lecture. I think it's going to be maybe two parts because there's a certain thing like I need to explain the whole circuit, but this is just like the intro to the parts of the circuit. Welcome to the lecture, DC motor speed controllers for favorite older brothers. Oh, oldest brothers. Sorry. By the end of this lecture series, you should be able to name and identify the role of key components in a DC motor speed controller circuit. 2. Identify the parameters that one needs to consider while selecting components. And 3. Understand best practices for creating and implementing DC motor controller circuits into your projects. Part 1. The components of a motor controller. The components of a DC motor controller outside of the motor and the power source. There are many important components that make up a motor controller. I'll explain what each does later. However, I will list them out first. This is an example of the completed circuit diagram, and I'll come back to that later. Different components. We have a 555 timer. It is what is called an integrated circuit. You might see it IC written next to it. We have a metal oxide semiconductor field effect transistor, which is just called a MOSFET. We have diodes, but flyback diode. We have a resistor. We have potentiometers and capacitors. Okay. Let's start with the 555 timer. The secret behind a DC motor control circuit is the 555 timer. This is what is called an internal circuit, meaning there is nothing intelligent about this chip. It is simply a circuit that is hidden under one housing. The internal drawing of the 555 timer can be seen here in the bottom right of the screen. The purpose of the timer is to send a pulsed voltage to the motor. These pulses can be imagined as being on or off. The motor will then speed up or slow down depending on the duration of these pulses. I will explain how we can control the duration of these pulses later. For now, just know that the timer's job is to send pulses towards the motor. This is what a 555 timer looks like in the top right. It has 8 pins. And then this is, so for example, the 8 pins are labeled here. So there's pin 1, pin 2, pin 3 is over here, 4, 5, 6, 7, and then 8. And that's each of those correlate with that. And then the dotted line correlates with the black box. But, as you can see, the outputs are on 4 different sides here. That's not accurate to this. Okay. The second thing is a metal oxide semiconductor field effect transistor, which sounds crazy, but it's very easy to understand how they got the name. And I'll explain how they got the name after. So a MOSFET is a special kind of electronic switch. The reason behind needing a MOSFET in the circuit is due to the limited amount of current that can actually flow through the 555 timer. While the limit is variable between manufacturers, often the current limit is 1/4 of an amp or less. So, to avoid frying the 555 timer with the full current of the motor, we use the 555 timer to pulse the MOSFET. Remember, it's a switch that is controlled electronically to open and close the circuit, allowing the motor to run. In summary, the 555 timer pulses the MOSFET, and the MOSFET pulses the motor. The reason is it's called a metal oxide semiconductor field effect transistor. It's from the it's from the top down. So if we look at the very top layer of this drawing of a MOSFET, there is metal. And metal is conductive, and the metal is connected to the gate pin. As you can see, there's 3 pins here. The furthest left is gate, then it goes drain, and then source. So we have metal, and then below the metal is oxide. It's silica oxide, and that is not conductive. So there is effectively an air gap between this metal and the rest of the region, the P-type substrate, but you don't need to worry about that, the bottom of it. But what we can do is, by applying let me go through the name again. Metal is the top, oxide, the layer below it. Semiconductor is the P-type substrate. Field effect is talking about there's a magnetic field that when we put a voltage on the gate, remember voltage is like pressure in a water line. You can have voltage without current because you can have, just like you can have water pressure without flowing water. And so we apply a voltage to the gate, and that voltage it creates a magnetic field that pushes a region of like grumpy electrons that don't want to participate down and away from the center. And then that gives room for happy electrons that want to go from source to drain to flow across. So by increasing that field, we can reduce the resistance between the two areas, allowing for more flow. Less resistance, more flow. So the gate creates a magnetic field that allows for the source and drain to effectively touch each other and flow between them. And the amount of flow is proportional to the voltage applied to the gate. There is a threshold minimum on the gate voltage because if it doesn't push enough to allow for one side to connect to the other, it's not going to have flow. So it has to push enough so that there is flow, and that's what's called the bottom threshold, or it's not, I don't know what they call it, but that's the bottom. That's what I would call the bottom threshold. And then there's a top threshold too, because effectively, you can only make it so easy to flow across. So that's what it is. It's a MOSFET. It's a special switch, and the switch is controlled by putting a voltage on the gate, allowing for happy electrons to move across by pushing the bad electrons with a magnetic field. It's very cool, very clever too. Okay, so we use the 555 timer to pulse the MOSFET, and the 555 timer is pulsing the gate. So it's pulsing, 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 and that increases or decreases how much flow is going through, which means the motor will take an average of how much power it can get over time, if that makes sense. Because we can vary how long these pulses are. So we can increase how often the motor is quote unquote on, even though to our eyes and our speed of processing, it looks like it's always on. It's just slowing down or speeding up. This is the same thing we do with lights. We don't dim lights. We can't like make it do less light. What we do is pulse the light so that it is on and off more or less often. That's what dimming is. This is the same thing. I mean, it's like a different technology, but it's the same exact idea. We dim lights by turning them off more often, which is kind of funny. Okay, so here's a general note before getting into the third thing. This is a general note on diodes. So diodes are a form of semiconductor that allows current to only flow in one direction. This is why LEDs, or light-emitting diodes, have polarity and only work when current is flowing in one direction. Diodes are used for many cases, but the case that you would be most familiar with is most likely the full bridge rectifier in a vehicle. The alternator in the vehicle generates three-phase AC power. To convert AC power to DC power, each phase of the alternator is fed into diodes. They each have their own diode. While A phase is pushing forward, its diode allows for electricity to flow towards the car battery to charge it. However, when the phase has slowed down to reverse, when the phase has slowed down to reverse, the diode prevents the A phase from pulling electrons from the battery. As the A phase is slowing down, the B phase speeds up and begins to go forward into its diode, feeding the battery, while the A phase is in reverse and no longer feeding the battery. This process repeats for the C phase of the alternator until it loops back to the A phase pushing forward again. This provides a constant current in one direction, which is also known as direct current. This charges the battery, and then the battery later releases the current in a cleaner and more regulated form as a 12-volt power source. The reason I needed to give that was the third item is flyback diode. A flyback diode, prevents flyback. Motors are considered inductors. While inductors running, they store energy in a magnetic field that is generated around the coils of wire. L in the diagram. The electronic symbol, to remember it, that's coils of wires cut in half. It's like as if you coiled wire in a spiral and then cut it in half vertically, or like lengthwise. That's why it's like that. That's an inductor. That's what that means. Okay, so L in the diagram. When power is removed from an inductor, the magnetic field suddenly collapses, and as the field pushes in on the inductor, the motor, it pushes electrons out in both directions from the motor. This sudden, inrush of current on other things, but outrush of current will destroy sensitive components that are electrically connected to the motor. To avoid this, we use a special type of diode that can handle those high inrushes of current, called a flyback diode, to reroute this sudden release of energy away from the sensitive components. The sensitive component that they are trying to protect in the diagram to the right is labeled T sub 0. The diode is inside the orange box. Notice the arrow and the wall. This is saying power can flow this direction, but it can't flow from left to right. The wall blocks it. The arrow allows it to flow through. The sensitive component that we are looking to protect in our circuit is the 555 timer. Okay. 4. A resistor. A resistor is anything that resists current, but while allowing the flow of current. So like wood isn't a resistor, but anything that allows electricity to flow through it can be a resistor. In fact, wires in the electrical trade, we have to calculate for their resistance if we're running long distances because it can affect voltage. Okay, so even wires can be a resistor because there's no perfect efficiency except for superconductors. But that's like, liquid nitrogen or whatever, liquid helium or whatever, freezing, that's not standard everyday stuff. Well, so a resistor is anything that resists current. While this could be a load, like a computer, vacuum, or light bulb, it can also simply be an electrical component called a resistor. It's called a resistor that has a fixed level of resistance. There are many use cases for this kind of resistor. The use cases vary depending on if you're wanting to regulate the voltage or the current of the circuit. I'll explain when and where we would use resistors later, but for now, you need to know that a resistor is an electrical component with a fixed resistance and can also be used to protect sensitive components. A potentiometer. A potentiometer is a variable resistor. This means that we can vary the resistance of the circuit without having to rewire it. Remember, depending on how it is used in a circuit, a resistor can modify either the voltage or the current at a specific point in our circuit. If you're following along, you might recognize something. I mentioned earlier that we can vary the pulse duration sent out from the 555 timer, and you might have made the connection, pun intended, that this is how we do it. A potentiometer in our circuit is used to indirectly control the period of our 555 timer pulses. Okay? And a capacitor. A capacitor stores electrical energy and releases it rapidly when given the chance. The main use of a capacitor in our circuit is to be an intermediary between the potentiometer and the 555 timer. The variable resistance of the potentiometer affects the how rapidly the capacitor charges up its energy. As soon as the capacitor has a charge larger than a threshold voltage determined by the manufacturer of the 555 chip, that's not clear, sorry. So this is controlled from the 555 chip. Sorry, I didn't proofread this. As soon as the capacitor has a charge larger than the threshold voltage of the 555 chip, determined by the manufacturer, let's say it's 8 volts, it will activate a transistor and an electrical switch. Remember, a MOSFET is also a transistor. Here, we'll go back. Notice field effect transistor. So transistors is an umbrella term, and there are subcategories. Of those subcategories are FETs, field effect transistors, that use that kind of mechanism there. There are other kinds of transistors that they do it in a different way, but it's still a way of controlling voltage. It's a way of like electrically controlling something with a third power source, a third and weaker power source. Okay, so we're saying that the capacitor is charging up, then through wiring, which I'll explain in this second video. The 555 chip is able to recognize if the charge of the capacitor, okay? And as soon as the 555 chip recognizes that the capacitor's charge has a larger threshold voltage, or a voltage larger than its threshold, we'll say for this example, 8 volts, it will activate, or it will close is a better way of saying that, meaning allowing electricity to flow. An open circuit doesn't work. A closed circuit flows, because it's like if you break open a pipe, it doesn't work anymore. It will activate a transistor, an electronic switch, inside the 555 timer, telling the timer to stop feeding the MOSFET that feeds the motor. When the capacitor is I apologize, but I want to explain this clearly. So let's say at this current moment, the MOSFET is feeding the motor, and the motor is running. It is waiting until there is an 8-volt charge on the capacitor. As soon as that 8-volt charge is found on the capacitor, it stops feeding the MOSFET and dumps the capacitor to ground. It says like, hey man, calm down, you're getting too excited. And while it's telling it, hey, calm down, you're getting too excited, it can't tell the MOSFET, hey man, keep running. Anthropomorphizing it, whatever. But that's what's going on. So while the timer is too busy saying, hey capacitor, calm down, it can't tell the MOSFET, hey, keep pulsing. So the MOSFET turns off, and that means that the motor would turn off. But these are short periods of time, so the motor isn't turning off. That's not right to say here. These cycles happen like I don't know how many times, but dozens of times a minute, a second. I mean, like a lot of times. So like it's on off, on off, on off. But anyway. So yeah, while it's telling the capacitor, hey man, calm down, it can't tell the MOSFET to feed the motor. As soon as it's calmed down to a lower threshold voltage of, let's say, 4 volts, it stops dumping the energy to the ground and says, okay, capacitor, go charge up, man. You're a little too calm for me right now. And then it can turn back to the MOSFET and say, hey man, give power to the motor. And then the motor would turn back on. And then that cycle repeats. The capacitor charges, it gets too much. The 555 timer dumps it to ground until it's 4 volts, and then it charges it up again. And this is the cycle of pulses that regulate the motor turning on and off. And as we turn the motor on and off, depending on how long it is off compared to how long it is on, that will determine the speed of the motor. So what we're trying to do is control how quickly the capacitor charges up, because that will determine our pulse width, or our pulse duration, which will determine the speed of the motor, because the speed of the motor is the average of the voltage applied to it over time. So if half the time you're applying 12 volts and half the time you're applying 0 volts, it will run as if it is at 6 volts. Okay? So we can affect these pulse durations using the potentiometer. The potentiometer allows the capacitor to charge quicker or slower depending on the resistance that we provide it. So if we create more resistance, the capacitor will charge slower, which means it is coming to the timer has to tell it, hey man, calm down, far less often meaning your motor is going faster. But if we decrease the resistance, the capacitor will be allowed to charge more often, meaning the 555 timer has less time to tell the MOSFET to pulse, or to go, and it has to take more time to dump the charge of the capacitor. This is the core fundamental part of a control circuit.